Hello all, welcome to the second video lecture on solar energy of module 3 energy engineering. The contents of the module 3 include solar energy, the fundamentals, the solar radiation, estimation of solar radiation on horizontal and inclined surfaces, then measurement of solar radiation data. Then we look at the application of solar energy into solar thermal systems, the flat plate collector, evacuated tube collector, solar air collector, the solar concentrator, distillation, solar cooking, refrigeration and air conditioning, then energy storage system. Further, we looked at the solar photovoltaic system, the introduction, solar cell fundamentals, the characteristics and its classification of solar cell into module, panel and an array. Then we looked at photovoltaic thermal systems. In this video lecture, we focus on solar radiation, then the estimation of solar radiation on horizontal surfaces and on inclined surfaces. The rest of the contents have been covered in the previous video lecture. Please consider subscribing to the channel if you haven't subscribed yet, so that you get all the updates and you get to enjoy the learning. Understanding of the estimation of solar energy requires understanding of the solar radiation geometry. The radiation geometry has certain set of angles that are generally used. So phi refers to the latitude of the location, delta represents the declination, omega the hover angle, alpha the altitude angle, theta suffix z, theta z the zenith angle, gamma suffix s the solar azimuth angle, and beta the slope. So these are the notations that are used widely, and we are going to follow the same. Phi refers to the latitude of the location, that is the angle made by the radial line joining the location of the earth to the center of the earth with the projection of this line on an equatorial plane. So consider an equatorial plane and project the line from the center of the earth. You can see here projection 1 P1, and then the angle made by the line that is joining the projection of the line. So this P, the angle between P and P1 is a measure of phi, the latitude. The latitude is measured as a positive number for a hemisphere, northern hemisphere, and varies from negative 90 to positive 90, and for southern hemisphere it is usually in the negative. The declination is the angle made by the line that is joining the center of the sun and the earth's projection on the equatorial plane. So it is the angular distance of the sun's rays, that is north or south of the equator. Its value usually varies from positive 23.4 to negative 23.4, and it is usually 0 on the equinox days, that is the March 21st and the September 22nd. The declination is usually calculated using the expression 23.45, sine of 360 by 365 into 284 plus n. This is an empirical relationship that is obtained, where n is the day of the year counted from 1st January, that is n is equal to 1, 2, 3, etc. etc. It is to be noted that for a leap year, that is the February, we will have 29 days instead of 28 days. Omega or the hover angle, it is the angle through which the earth must rotate to bring the meridian of the point directly on inclination with the sun's rays. So meaning the earth must be rotated in such a way that the meridian points directly with the inclination of the sun's ray. It is usually equal to 15 degree per hour and varies from minus 180 to plus 180. So in the morning times it is negative value, and at noon it is 0, and as it traverses, as the evening sets, it is positive value, and usually evaluated by omega is equal to cos inverse of minus tan phi tan delta, where phi is the latitude, delta is the declination, that is calculated using the expression here. Altitude angle, it is the vertical angle between the sun's projection on the horizontal plane and the direction of the sun's rays. This is important to see what is the path of the sun that it takes. Usually the summer the sun's altitude is higher, and in winter the sun's altitude is little lower. This helps in designing of the systems and to do a shadow analysis of the solar photovoltaic systems or solar systems in general. The zenith angle, it is the vertical angle between the sun's rays and the line perpendicular to the horizontal plane through a particular point, that is theta z, given by 90 minus alpha. So again, theta is 90 at the sunset and minus 90 at the sunrise, and the zenith angle here is the theta, that is shown as theta here in the image and theta z here, and we use theta z as the notation. The solar azimuth angle, it is the angle made in the horizontal plane between the line due south and projection of the site of the line. So what it essentially means is you take the sun's radiation, you project it onto the south, and from the north, which when you measure this becomes the azimuth angle. So represented, and it is evaluated by the expression as cos theta z. Theta z is the zenith angle, sin phi is the latitude, sin delta declination angle, and in the denominator it is sin theta z and cos. Slope, it is the angle made by the plane with respect to the horizontal, that is the angle through which the systems are inclined. Theta is the incident angle, that is the angle measured between the beam rays normal to the plane, given by this expression. Although it is lengthier, there are certain variations for this. For example, when the slope is 90 degree, the expression is reduced to this, and when the slope is 0 degree, the expression is reduced this. And for a surface that is facing due south, the azimuth angle becomes 0, and then the expression is this. This is the most widely used expression to calculate the beam radiation or calculate the incident radiation on a particular surface with when the surface is facing due south. So this expression is taken as the expression for the incident. So all angles summed up into one single diagram. So pause for a moment and understand these angles, so it is better for solving the numericals. The next is the day length. It represents the passage of the time based on the sun's position in the sky, evaluated by the expression 2 by 15 cos inverse of minus tan phi tan delta. We now look at the sample numericals. Here calculate the angle made by the beam radiation with normal to a flat plate collector on December 1 at 09 hours, that is the local apparent time LAT. The collector is located in New Delhi. The latitude and the longitude is given and is tilted at an angle of 36 degree with the horizontal and is pointing due south. So also find the day length. So what data is given? December 21, so that is n that can be obtained through this, and local apparent time is given 09 hours. Then the collector is located at a particular latitude phi, then tilted at an angle of 36 degree, that is nothing but the beta, that is the slope, and is pointing due south. So this pointing due south, gamma is 0, beta is 36, phi 28 degree 35 minutes converted into degrees in the calculator 28.58. For December 21, n is 355. This is taken by excluding the date of December 21, so we get n as 355. We first find out the declination, that is 23.45 sin 360 by 365 into 284 plus n. Substitute n as December 21st, n as 355, so we get delta declination as minus 23.45. So also for the 9 hours of local apparent time, omega is taken as 45 degrees. And then for the angle that is facing due south, the incident angle is obtained by this expression. Substitute all the relevant values: phi delta, phi the latitude which is given, beta which is also given, that is the slope, declination calculated, omega is calculated, substitution, then finding the theta. So the theta comes out to 46 degrees, that is the angle incident here. Then the day length is evaluated using this expression: dt is equal to 2 by 15 cos inverse of minus tan phi tan delta. So this works out to 10.17, that is the hours. The unit of day length is hours, or converted into degrees and minutes, 10 hours and 10 minutes. The second numerical: calculate the angle of incidence of a beam radiation on a plane surface tilted by 45 degrees and pointing 30 degrees west of south, located at Mumbai at 1:30 p.m. The IST or the LAT that is given on 15th November. The latitude and longitude is given, and the standard longitude is also given here. So for November 15, N becomes 319. Latitude is 1330 hours. Local apparent time is 1330 hours. And here the surface is not pointed due south, so there is a particular angle that is 30 degrees. And then beta is 45, the slope. Then phi latitude is 18 degree 54 minutes, converted into degrees 18.9. When the standard longitude data is available, the LST may be used for calculation, and that is we look at how to do it. So first we calculate the declination 23.45 sine 360 by 365 into 284 plus n. So n is 319. We end up getting the declination as minus 19.2. The next is omega. To calculate the hour angle, we make use of this local time. The expression is given by this: the solar time is equal to standard time plus or minus 4 times latitude of the standard place and latitude of the location, which is taken in minutes, and then equation of time correction. Here the equation of time correction is not provided, hence it is omitted. So the solar time is the standard time, that is given as 1330 hours or the IST, and then 4 into the standard longitude 81.73, that is given here. It is 81 degree 44 minutes, that is converted to decimal values 81.73, and then latitude of the location, that is given as 72 degree 49 minutes, converted into decimal value 72.81. So 13 hours 30 minutes minus 36 minutes. So here the solar time here which is obtained is subtracting the time here. So 30 minutes, 36 minutes. So we are left out with 12 hours 54 minutes. Now we find omega, that is given by omega 12 minus the solar time into 15. Note that the solar time has to be kept in hours only. So 12 degrees minus 12 degree 54 minutes into 15. So omega turns out to be minus 17.25. The previous numerical, there was no standard time or the longitude that is given. Hence, we took omega directly in terms of the angles 15, 30, 45. So for 9 o'clock, it was 45 degrees. So here we end up calculating using this expression. So these are the additional steps that need to be employed to calculate omega when the equation of time correction or the standard latitude and longitude is usually given. So finally, an expression of incidence of beam radiation, and there is omega existing and there is gamma existing, and given by this expression, and all values of been found. When we substitute, we end up getting the angle of incident beam radiation as 37.22 degree Celsius. The third numerical, the angle made by calculate the angle made by the beam radiation with normal to a flat plate collector, which is pointing due south, located in Bangalore. The latitude and longitude is given at 9 a.m. on December 1st. The collector is tilted at an angle equal to the latitude, and the standard IST is given. Equation of time correction is also given here. So in this numerical, further what is given is the collector is pointing due south, so gamma is 0. Then the latitude is given, the time is given. Then collector is tilted at an angle equal to the latitude. So beta is same as the latitude, that is 12 degrees 58 minutes. So the standard time, and also further the equation of time correction is given here. We look at how to solve it. December 1, so n becomes 335. Then LAT 9 hours, morning 9 o'clock. Gamma is 0, so they've given it, and it is pointing due south, hence it is taken as 0. Then phi 12 degrees 58 minutes converted to decimals, so 12.97 degrees. So the slope is same as the latitude, so beta is also 12.97. Then equation of time correction is given as minus 1 degree 1 minute, so same converted to decimal places. The first one, declination is calculated. So 23.45 sine 360 by 365 into 284 plus n. So n is substituted with 335. We end up getting declination as minus 22 point. Further, we calculate the solar time given by the expression standard time plus or minus 4 times the longitude of the standard value minus the longitude of the location, that is to be taken in minutes, and the equation of time correction. Here the numerical has the value of equation of time correction, which is given as minus 1.01 minutes. So we consider the same. Thus we end up calculating the solar time as this. So we get the solar time as 8 hours 42 minutes. Further, we calculate the omega, that is the hour angle, given by the expression 12 minus the solar time, that is to be considered in hours, and multiplied by 15 degrees. So 12 minus 842 into 15, we get the omega as minus 49.5 degrees. Further, we obtain the value of theta by this expression. We consider this expression because it is given that the collector is facing due south, hence gamma becomes 0, and we end up using this expression. When we substitute all the values, we get theta as 53.1 degrees. That is the angle that is incident on the as a beam radiation. Thanks for watching this video. This video has covered all the numericals, typical numericals that are asked from the examination point of view, along with the